You've just opened the most precise and mind-stretching breakdown of what really happens at the edge of a black hole. Every moment in this video is packed with what you came to find. You're exactly where you need to be. At the very border of space and time, reality begins to twist, and what you thought you understood no longer applies. Get clear answers on where matter goes, what happens to time, and how the universe might store secrets on the surface of darkness itself. Space holds places where the laws of nature bend in strange and powerful ways. One of these places is called the event horizon, a silent, invisible line wrapped around the heart of a black hole. It is not a physical surface, yet it holds a powerful effect. When something crosses this point, it vanishes forever from the visible universe. No signal, no light, and no message can come back. It marks the boundary between what can still influence the outside world and what is locked away in darkness. The event horizon is the edge of our understanding, and what lies beyond is still a mystery even to science. The pull of gravity becomes extreme near the event horizon. Space stretches, time slows down, and matter begins to act in ways that defy ordinary logic. Scientists believe the event horizon hides deep truths about the universe. It may hold the key to uniting the strange world of quantum physics with the large-scale world of general relativity. These two ways of describing the universe have never fully agreed, but the event horizon may be the place where they come together. Despite the darkness, we are starting to learn more. With powerful telescopes and clever math, we've seen shadows of black holes, patterns of light swirling nearby, and even the outlines of the horizon itself. Each discovery leads to more questions. What happens to information that falls in? Does time stop at the edge? Are these mysterious boundaries smooth, or are they blazing hot with energy? Let us explore the most important ideas and mysteries about the event horizon, from how it forms to how it might help explain the deepest truths of space and time. A line drawn in space that cannot be seen or touched can still decide the fate of everything around it. The event horizon is that kind of line. It surrounds a black hole like an invisible shell. Once anything crosses this shell, it can never return. Even light, which moves faster than anything else in the universe, cannot escape once it crosses this line. That's why the inside of a black hole remains hidden from view. The event horizon acts like a one-way door. Objects can enter, but they can never come back out. It is the edge of no return. The reason this happens lies in gravity. A black hole's gravity is so strong that at a certain distance, escape becomes impossible. This distance is what defines the event horizon. If you try to fly away from it using rockets or scream for help with a beam of light, nothing will make it out. Your speed would need to be faster than light, and that is something nature does not allow. So the event horizon becomes a boundary of isolation. Anything beyond it is lost to the universe forever. The event horizon is not made of matter. It's a place in space-time where the rules change. An object falling toward it would not feel anything special at the exact point of crossing. It wouldn't bump into a wall or pass through a gate. But to an outside observer, it would appear to slow down, freeze, and fade. This strange effect makes the event horizon more than just a distance marker. It's a place where time and space behave in unexpected ways. The event horizon is not just a location. It is an idea made real by gravity. It's where space curves so deeply that escape becomes impossible. It marks the limit of what we can observe and the start of what we can only guess. The event horizon is not just a boundary in space. It is a border where the laws of escape break down completely. If you cross it, you are trapped forever. The escape velocity at this point is faster than the speed of light, and since nothing in the universe can go faster than light, there is no way back. A spaceship, a photon, or even a signal of warning, none of them can fight their way out once this line is crossed. It is the ultimate no-return zone, the final frontier in a very real sense. What makes this so extraordinary is how calm the crossing feels. To the person or object falling in, there is no crash, no bump, no alarm. You simply float past an invisible line, unaware that you've left the known universe behind. But from the viewpoint of someone far away, things look very different. The falling object slows down, becomes redder in color, and fades from sight. It seems to freeze in time just outside the event horizon, never quite crossing it. This illusion is caused by extreme gravity bending both light and time. This difference in views is not just strange, it's a key feature of relativity. The event horizon marks the boundary where these differences become permanent. Outside observers can never see what happens past the point of no return. They can only guess. The very concept of after becomes twisted by the bending of time. Once you're inside, your future ends at the center of the black hole. The point of no return is where freedom ends and destiny begins. It's not just a location, it's a decision made by gravity that can never be reversed. It is the ultimate divide between light and darkness, between the seen and the forever hidden. Time does not flow at the same rate for everyone. In normal life, this effect is so small we never notice. But near the event horizon, time becomes strange and twisted. As gravity grows stronger, it pulls not just on objects, but on time itself. A clock ticking near the event horizon will slow down compared to a clock far away. The closer you get to the edge, the slower time moves from an outside view. If someone were to fall toward the black hole, they would seem to freeze in place to a distant observer. This time trick is part of Einstein's general theory of relativity. It tells us that gravity is not just a force, it is the bending of space-time. Near a black hole, this bending becomes extreme. A single second near the event horizon could stretch into minutes, hours, or even centuries from the perspective of someone far away. In theory, someone orbiting close enough and surviving the dangers could return to find the universe changed beyond recognition. For the person falling in, nothing feels wrong. Their heartbeat, their thoughts, their fall all seem normal, but the rest of the universe appears to race ahead. Galaxies spin faster, stars die, civilizations rise and fall, all in what feels like moments. This effect makes the event horizon a kind of time machine, though one that only works in one direction. Time slows for the traveler, but keeps moving for the rest of the universe. The event horizon becomes a place where time stretches so far that the present and future blur. It turns time into a slippery and uncertain path. The closer you fall toward a black hole, the more violent the pull becomes. Gravity does not pull evenly. It pulls more strongly on the parts of you that are closer. If your feet are closer to the black hole than your head, your feet will feel a stronger force. This stretching of your body turns into something terrifying. Scientists call it spaghettification. You are stretched into a thin line, like spaghetti, while being squeezed from the sides. It sounds like science fiction, but it is a real prediction of physics. This effect depends on the size of the black hole. Small black holes have sharp gravity near the event horizon. If you fall into one, you are torn apart before you even reach the event horizon. Larger black holes have gentler gradients near the horizon, so you might pass through the edge unharmed, only to be stretched later as you move deeper. Either way, the final result is the same. The powerful differences in gravity rip you apart. Spaghettification shows just how extreme things get near the event horizon. It's not just time that bends. Space itself becomes dangerous. Forces that are harmless on Earth grow so powerful that they can turn solid matter into long, thin strings of atoms. Even light, which usually flies in straight lines, curves and spirals inward. The black hole does not pull like a vacuum cleaner. It reshapes the very fabric of space around it. Spaghettification is a vivid symbol of this strange and deadly world. Not everyone sees the same thing at the event horizon. This is one of the most surprising parts of black hole science. For someone falling in, the journey is smooth and quick. They do not feel the event horizon, they simply pass through. But for someone watching from far away, the story looks very different. They see the falling person slow down, grow redder, and eventually vanish. This difference in experience is not just confusing, it is a deep part of how the universe works. To a distant observer, the falling person never really crosses the horizon. Instead, they appear to hover at the edge, frozen in time. Their signals become weaker and redder, stretched by gravity until they fade completely. But the falling person experiences nothing unusual. They keep going. This split in what is seen comes from time dilation and gravitational redshift, both predicted by relativity. This means that what happens at the event horizon depends on where you are. There is no single story that fits all views. The horizon is a mirror, a boundary, and a puzzle all in one. It shows how extreme gravity tears apart not just space, but reality itself. Events can happen and not happen depending on your point of view. The event horizon breaks our usual ideas about space and time. It forces us to think in terms of frames and relativity where truth depends on position. A deep mystery surrounds the question of what happens to information when it falls into a black hole. In everyday life, when something is destroyed, like a burned book, the particles are still there and in principle the information can be recovered. But when something crosses the event horizon, it seems to disappear entirely. It's not just the object that vanishes, but also the information about its shape, structure, and even what it was made of. This creates a puzzle that challenges the foundations of physics. Quantum mechanics tells us that information cannot be destroyed. It is one of the core rules of how the universe works. Every particle interaction must preserve the record of what came before. But general relativity allows a black hole to swallow information forever. These two rules don't agree, and the event horizon is where their clash becomes unavoidable. If information is lost, quantum physics breaks. If it is not lost, then somehow the information must escape a place where nothing can escape. This conflict is called the black hole information paradox. Some scientists believe the information is smeared across the event horizon in hidden quantum patterns. Others suggest it may be stored in the Hawking radiation that leaks from black holes over time. Another theory says that the event horizon may not be smooth and quiet, but full of energy and fire, a firewall that destroys everything, even information. These are not just ideas. They challenge the very rules we use to understand the universe. The question of what happens to information remains unsolved. It sits at the crossroads of relativity, quantum theory, and thermodynamics. The event horizon, quiet and invisible, becomes a battleground where the deepest truths are still waiting to be uncovered. Whether it stores information, transforms it, or hides it forever, the answer could reshape our understanding of reality itself. An invisible black hole might not stay invisible forever. In 1974, Stephen Hawking made a discovery that shook the world of physics. He showed that black holes are not completely black. They can leak a faint glow of particles into space, known as Hawking radiation. This happens because of strange effects near the event horizon, where quantum rules allow particles to pop into and out of existence. Most of the time, these pairs of particles cancel each other out. But near the horizon, one can fall in while the other escapes. When this happens, the escaping particle carries away a tiny bit of energy. Over time, this process causes the black hole to lose mass. If it goes on long enough, the black hole could eventually evaporate entirely. The idea that something as powerful and final as a black hole can slowly disappear changes everything. It means that the event horizon is not a perfect trap after all. This radiation is extremely weak for large black holes, and it is almost impossible to detect with current tools. But the theory behind it has led to major changes in how scientists think about gravity, quantum fields, and the fabric of space. Hawking radiation is not just a prediction, it is a clue. It shows that black holes might not keep secrets forever. It suggests that information might escape in a disguised form. It hints that black holes obey rules similar to hot objects with temperature and entropy. Hawking radiation connects the event horizon with the deepest puzzles in physics. It is a bridge between Einstein's curved space-time and the uncertain dance of quantum particles. The event horizon, once thought to be a perfect wall, turns out to have cracks that leak light and meaning into the universe. The idea of a firewall sounds violent and sudden. It suggests that something horrible might be waiting at the event horizon. In 2012, a group of scientists proposed that the smooth crossing of the horizon might not be smooth at all. Instead of passing through calmly, anything falling in might be hit by a wall of energy that tears it apart. This goes against earlier ideas where the event horizon was seen as silent and uneventful. The firewall theory was meant to solve the information paradox, but opened a new problem instead. The firewall appears when trying to protect the rules of quantum mechanics. If information cannot be lost, and if Hawking radiation carries it away, then something strange must be happening at the horizon. The old view said the horizon was just an empty shell, but to save the rules, the new view says the horizon must be active and dangerous. The firewall would destroy anything that touches it, violating the old rule that falling into a black hole feels normal. This idea caused a storm in the world of physics. It challenged the principle of relativity. which says that the laws of physics should look the same for someone in free fall. It also questioned our understanding of space and time near extreme gravity. Most physicists agree that either the firewall is real or something even stranger is hiding at the edge. The event horizon, once thought to be passive, may be full of activity. Whether the firewall exists or not, it shows that we are still far from fully understanding what happens at the edge of a black hole. It is a place where the most basic ideas in physics may need to be rewritten. Albert Einstein's general theory of relativity changed how we see the universe. It showed that gravity is not just a force, but the bending of space and time. In this new picture, a black hole is not an object in space. It is a region of space where the bending becomes infinite. The event horizon is the invisible border of this region. It is the place where space curves so much that all paths lead inward. Nothing can escape, because escape would require outrunning the shape of space-time itself. In general relativity, the event horizon is not made of matter or energy. It is the point where light rays that are just barely aimed outward no longer move outward at all. They hover, frozen in place, held still by the pull of the black hole. Just beyond this point, even light begins to fall inward. The event horizon marks the edge where the flow of space-time turns completely inward, like a waterfall pulling everything into a pit. The math of general relativity predicts the event horizon naturally. It appears in the solutions to Einstein's equations when mass is packed into a small enough space. These equations tell us that a massive collapsing star can warp space so much that it creates a horizon. Once this horizon forms, nothing inside can affect the world outside. The region is cut off. The horizon becomes a one-way surface that separates two parts of the universe, outside and inside. Relativity also shows that the event horizon has a shape and size that depend on the mass of the black hole. More mass means a bigger horizon. But the rules that apply to the horizon are the same for all black holes. This shows the power of general relativity. It creates a picture of the universe where space can fold in on itself and create boundaries made entirely of geometry. At the edge of a black hole, the calm surface hides a restless world beneath. Quantum mechanics tells us that empty space is not really empty. It is full of particles flashing into and out of existence. This buzzing sea of activity is especially wild near the event horizon, where extreme gravity changes the rules. The uncertainty principle means we can never know exactly where a particle is and how fast it is moving. Near the horizon, this fuzziness becomes intense. Quantum fields near the event horizon interact in unexpected ways. Sometimes pairs of particles appear from nothing. One falls into the black hole and the other escapes, creating Hawking radiation. But even beyond that, the quantum fields themselves become distorted by the intense warping of spacetime. This means the vacuum near the horizon is not quiet. It is noisy with activity we cannot directly see. These effects matter because they raise questions about the structure of space itself. Is the horizon sharp or fuzzy? Is it a smooth surface or a layer of tangled quantum energy? Some theories suggest that information is stored in these quantum ripples at the horizon. Others think the horizon is a projection from deeper dimensions where the uncertainty spreads across more than just our visible space. The event horizon is where quantum mechanics and gravity meet head-on. Each has its own set of rules, and they do not always agree. The horizon becomes a testing ground for new ideas like quantum gravity, string theory, and loop quantum cosmology. It is a place where uncertainty becomes more than just a rule. It becomes the fabric of reality. What lies there may one day explain how the universe really works. When something falls into a black hole, its details vanish. This is one of the strangest ideas in physics. According to the no-hair theorem, a black hole can be completely described by just three things: its mass, its spin, and its electric charge. All other details, its shape, composition, or history, are erased. No matter what falls in, the black hole forgets everything except those three traits. A planet, a star, or a spaceship. Once inside, they all become the same. This means black holes are the most simple objects in the universe. They have no surface, no rough edges, no distinguishing marks. They are like smooth, featureless spheres. The event horizon covers up the chaos inside and hides all the details. This is why the idea is called the no-hair theorem, because black holes have no extra features or hair to describe them. The simplicity of black holes makes them useful for study, but it also creates problems. If all information is lost except mass, spin, and charge, then what happens to the rest? Where does it go? If black holes have no memory of what they swallowed, it means information is lost, which goes against quantum theory. So, the no-hair theorem may be true but incomplete. Some scientists believe that black holes do have subtle quantum features that can carry extra information. These features might live on the surface of the event horizon or in the patterns of radiation that escape. But until we understand quantum gravity better, the no-hair theorem remains a strange and powerful idea. It shows how black holes are both the most extreme and most elegant objects in the cosmos. A surprising idea in modern physics says that everything inside a region of space might be fully described by what's happening on the boundary of that space. This is the heart of the holographic principle. When applied to black holes, it suggests something astonishing. All the information about what falls into a black hole could be stored on its event horizon, not inside but on the surface. Just like a hologram on a flat card can show a three-dimensional image, the horizon might hold the full story of what lies within. This principle helps solve one of the biggest puzzles in physics, the information paradox. If the information about fallen matter isn't lost but spread across the surface of the horizon, then quantum mechanics remains intact. The event horizon acts like a recording surface. Even though we can't read the information yet, the universe might still be keeping it safe. The holographic principle comes from string theory and ideas about black hole entropy. In the 1970s, scientists found that the entropy of a black hole, the measure of its hidden complexity, depends not on its volume, but on the area of its surface. This was strange because most objects get more complex the bigger they are inside. But black holes follow a different rule, as if their entire contents are painted on their outer shell. This principle doesn't just apply to black holes. Some physicists believe the entire universe might be a kind of hologram. Everything we see and touch could be a projection from a deeper, flat reality. The event horizon becomes more than just a boundary. It becomes a canvas that holds the deepest information in the universe. If true, this idea could change how we see reality itself and reveal that space and gravity are not fundamental, but created by deeper forces we are only beginning to understand. For a long time, black holes were just mathematical predictions. They couldn't be seen, only inferred from the movement of stars and light. But that changed with the Event Horizon Telescope, a global network of radio telescopes working together to capture the unseeable. In 2019, the world saw the first ever image of a black hole. It wasn't a photograph of the black hole itself, but of the light surrounding it, shaped by the shadow of the event horizon. That shadow confirmed what theory had predicted. The telescope used a technique called interferometry, linking observatories from across the Earth to act like one giant dish the size of the planet. This allowed it to detect incredibly fine details in the radiation near the event horizon of a supermassive black hole in the galaxy M87. The image showed a bright ring of glowing gas with a dark center, the shadow of the black hole. The size and shape of that shadow matched what Einstein's equations said it should be. This discovery was a turning point. It showed that event horizons are not just theoretical ideas. They shape the behavior of matter and light around them in real, measurable ways. The image captured how space bends under extreme gravity and how photons whirl in tight loops before being pulled in or flung away. The Event Horizon Telescope continues to study other black holes, including the one at the center of our own galaxy. Each new image helps test our understanding of gravity and space-time. The event horizon, once invisible and silent, has now become a target for observation. It proves that even the darkest parts of the universe can leave behind visible signs, and science has found a way to see the unseeable. Everything outside the event horizon can still influence the universe, but once something crosses that border, it moves into a region that is cut off from everything else. The inside of the event horizon is a place no signal can escape. It becomes a prison of space where every path leads inward. Time itself changes direction. Instead of moving through space toward a location, you are dragged forward in time toward a final end point, the singularity, The singularity is the heart of the black hole, where gravity becomes infinite and the known laws of physics break down. Inside the event horizon, space and time switch roles. Moving forward in time always takes you closer to the center. You cannot stop, cannot turn around, cannot hover. Just like you can't stop aging on Earth, you can't stop falling once inside the horizon. No one knows for certain what truly lies beyond the horizon. We have equations, but no experiments. Once something falls inside, it is gone from view forever. All we have are theories. Some believe that space ends in a point. Others think the singularity may not exist as we picture it. Quantum physics might replace it with something less final, like a loop or a bounce. But without data, we cannot be sure. The event horizon shields us from this mystery. It hides the ultimate fate of matter and light. Inside the horizon may lie the key to quantum gravity, time travel, or entirely new laws of physics, but for now, it remains sealed, silent, and unreachable. Event horizons have never been touched, seen directly, or crossed by any probe. They are not surfaces made of matter. Instead, they are predicted by equations, especially those in Einstein's theory of general relativity. Some scientists argue that the event horizon is more of a mathematical boundary than a physical object. It exists in the geometry of space-time, not in the way a planet or a star exists. Yet despite this, its effects are very real. Light curves around it, matter falls into it. Time slows near it, and its shadow has even been seen by telescopes. There are theories in which event horizons don't really form at all. Some suggest that as a collapsing star gets close to forming a black hole, quantum effects stop the process just short of creating a true horizon. Other ideas replace the event horizon with something else, like a fuzzy boundary, a bubble of quantum chaos, or even a firewall. These theories try to fix the problems that event horizons create, like the information paradox, while keeping what's been observed. Despite the doubts, the event horizon remains the best working idea we have. It fits what we see in space. It explains the motion of stars around invisible centers of mass. It matches the image captured by the Event Horizon telescope. And it behaves in ways predicted by both relativity and thermodynamics. Whether it is a precise feature of reality or a useful approximation of deeper physics, it continues to guide research and shape our understanding of extreme gravity. As our tools grow stronger and our theories evolve, we may someday see more than just the shadow. We may find out what the event horizon truly is, a hard edge, a soft veil, or a crack in the rules of the universe that points toward something even more fundamental. The event horizon is not just a concept from science fiction. It is one of the most serious and mysterious features in the universe. It is a laboratory for the deepest questions of science. And we are reminded that even the simplest surface can hold secrets deeper than we ever imagined. The event horizon challenges our imagination and our science. It draws a line between what we know and what we do not yet understand. And it reminds us that the universe, in all its beauty and power, still holds many doors that have not yet been opened. Disclaimer. As an Amazon and other affiliate, I earn from qualifying purchases at no additional cost to you. Do you like the video and want to make videos like this? Turn text into stunning videos in seconds. Get free trial and unlock your creative potential. You can create even better videos than mine. No editor is required. Check out the link in the video description below. What do you think? How does the idea of an event horizon connect to anything in your own life? Let us know your thoughts or questions in the comments. And if there's a topic you want us to explore next, let us know. Your idea could shape our next video. Thank you for joining us on this journey through Event Horizon. Please like and share the video, and please do not forget to subscribe for more videos.